Okay, I guess we'll go ahead and get started. Thanks for sticking around to the end of the day, everybody. I know it's a long day at these things. It's exhausting listening to people talk at you. So for those who weren't at my first talk, my name is Austin Bingham. I work for and part own a small software development and consulting company in Norway called 60 North. And I'll be talking today about what I call the primacy of testability. And that's kind of a fancy name, a fancy title to get the talk selected at conferences, but really what this talk is about is using testability as a proxy, so to speak, what I call a barometer for helping you understand all the complexity in your architecture and helping you manage the compromises you invariably have to make when working with complex systems. This talk was originally aimed at software architects, but really it's for anybody concerned about things like non-functional requirements and quality attributes in their systems. And so hopefully this doesn't miss its target at this conference. So this is a hurricane. It's the nicest, coolest picture I could find of the Earth's atmosphere. The Earth's atmosphere has something on the order of 1 million trillion molecules in it. And we have people whose job it is to predict what that 10 to the 54th molecules is going to do every day. And we do a fairly good job of it, but we apply really powerful tools. We have, banks of computers, we have government agencies, we have satellites, we have, kind of the massive human technological capabilities aimed at understanding the weather. And we do a reasonably good job. A much simpler tool that gets you a long way is a barometer. All a barometer does is measure how much air is stacked above you at any given time. So with a barometer and a pencil and some paper and some time, you can do a pretty good job of predicting if it's going to rain or if it's not going to rain, that kind of stuff. You may not be able to predict the path of a hurricane with the barometer, but you can get a lot of the information you need, and it gives you a warning that a hurricane is coming or something else is coming. It's a useful, relatively crude, but great proxy tool for weather analysts. So I'm going to propose a metaphor that testability is a barometer for software architects, really a barometer for anybody concerned with monitoring the complex interactions, the complex trade-offs that go on in any piece of software, any non-trivial piece of software at least. Our job is to manage and foster and really shepherd the non-functional requirements in a system, and doing that is really hard. What makes that hard? A lot of people are working on multiple projects, especially at companies that have professional architects they're sitting sort of at the top of some design, and they may have to jump from project to project to project inside a day, maybe just in a week, but they tend to bounce around quite a bit. And that's cognitively very difficult to switch in and out all this information they have to deal with. They work on large, or what I call fast projects that are iterating very quickly and going through the design phase and maybe have complex changes happening inside of them. So what they knew last week, before they went off to work on project B, they come back to project A and a lot of things have changed. That makes it very difficult to keep track of all the little pieces, the threads in the system. There's complex interactions between things. I may be trying to make my system faster, and in doing so I can damage its security, or I can damage its scalability, or whatever. There's always these balancing acts between all of the different elements in a system that we have to deal with. Finally, it just amounts to mental overload. You just have too much going on and you stop being able to do your job effectively. Does this picture ring a bell with anybody? Everybody know what this is, that picture? If you do, you're old school, right? That's from Doom, yeah. So really, I'm going to propose that testability tells us about quality in an overall sense. Testability is in some sense vague. It's just a proxy. It's not a direct thing for the most part, but it's something that can tell us quite a bit about the systems we're working on. So paying attention to it, explicitly paying attention to it and tracking it and listening to what it's telling us is a really important thing we can do. We don't all have satellites and banks of supercomputers and government agencies looking at our code, except the NSA. They're looking at everybody's code all the time. It's a joke. But the testability is something that we can all get without high-tech tools like that, without investing in heavyweight machinery. So I'm going to set a few ground rules, just a few definitions to put us all on the same page. Sorry, this is a bit close there. What is a software architect? What am I talking about when I say software architect? There's 1,000 definitions for this, and this is what we spend most of our time at architecture conferences talking about, is what is a software architect? The job responsibilities, okay, drawing boxes and arrows, obviously that's what software architects do. That's an important part of it. Managing non-functional requirements, managing the illities in your system, scalability, modifiability, security, not really an illity, but it's in there. Importantly, and I think this is a really critical feature that's missed by some people, is that architects need to know how to code. Not just know how to code, but they need to be involved in the code bases they're working on a regular basis. They need to know what the moving parts are. They need to be able to be involved in the development. They should be expert developers, actually. They should be, architect means, master builder. So that's what an architect ought to be. They ought to be somebody who can go in there and get their hands dirty as well as manage the high-level things. And I'll touch on this necessity to be able to code a few times. It's a critical element, I think. It's missed by some companies, actually. Another definition is probably important. We have architects, so what is testability? This is a little bit of a vaguer one, actually. There's no great single definition for what is testability. You can read books, and they'll tell you they have a definition. Somebody else will have a different one, and they're both correct. The problem is testability really is the confluence of a whole lot of things, and so to give a single definition to it is always going to miss some point. I'm not going to try to give it a definition, but I'm going to look at some of the qualities of testability, and we'll use that as our platform for the rest of the talk. So, I think we all recognize and probably all agree that even if we can't define testability, we know that there's some code that's easy to test, some code that's really hard to test. You get some code that's to test it, you have to instantiate 1,000 things and talk to a satellite and an undersea cable and things like that just to make Hello World work. In other cases, it's really trivial to do an equivalent kind of test because things are modular or things are easy to understand. So without having an actual definition of testability, I hope we can all agree that there's some notion of a spectrum of easy to hard in testability. There are some things that correlate with testability. And these are literally taken from the wiki page for testability, our Wikipedia page for testability from about 2 years ago. So observability, that plays into making something testable. Heterogeneity, understandability, et cetera, et cetera. There's all these other illities that we say, okay, this tells us something about the testability of a system. So you can sort of tag these things onto the definition, but they are not the definition, I think. The ultimate important thing to remember is that testability has to be done by a person. I don't think we have the wherewithal right now to measure testability in any meaningful way with an automated tool. So robots can't do the job. And this is one of the big reasons that I think architects need to be able to code. Even if they're not actively coding all the time, they need to be able to understand the influence of a change on the testability of a system. And the only way to do that in this day and age, the state of maturity of our industry, is to understand code and understand it really, really well. So this is one of the primary reasons, I think, and it's stressed, that architects need to be able to code. So finally, why testability? Why is this important? I've just finished telling you that testability is really difficult to measure, vague, and requires a super expert, an expert master developer to really come to grips with. So maybe working with testability is not worth the effort. Maybe it's too expensive. What's worth remembering, and really critical, is that testability is very, very special. Sorry, I put that down there. Testability is essentially your first customer in most situations. Not a customer in the sense that they're paying you for software, but the sense that they're the first user of your API or your product or your web page or whatever it is. You write it, it goes to test. If you want to get immediate feedback, that's where you get it from. And ignoring that feedback, ignoring what it's telling you about the qualities of your system, is losing an important signal in your development process and basically throwing away information and therefore throwing away money in the design process. So it's exercised early, it's exercised often. I'm talking about your tests. And so that's the reason that I really feel that it's something we should stress more, we should try to understand more and leverage more in our work. Now you'll notice that I made a subtle shift a few seconds ago. I was talking about testability, and all of a sudden I started talking about something being tested. And in principle, you could argue that you could have highly testable code that has no tests. You could do that. And I think that that's it's an impractical argument to make. It just doesn't happen in real life. People with testable code tend to have lots of tests because there's a relationship between tests and testability in real world and the way they kind of feed off of one another. So when I say testable for this talk, I mean tested. If you want to argue about that or have a discussion about it, I'd love to, because maybe I'm wrong in some of my assumptions, but this, in my experience, is the case. So testable code means tested for the rest of this talk. So I'm going to dive right in. There's not a huge amount of time for this. So quality is correlated with testability. I want to look at a handful of the ilities and the principles that we use in software development and see how they're associated or correlated with testability. And understanding these correlations and relationships are what allow you to understand the output, the results of your testing experience, and see what they're telling you about the rest of your code. Modularity is probably the easiest. Modularity is what we'll talk about first. It's the easiest one. It's the low-hanging fruit. It's the apple that a child can pick because it's obviously related to testability in many ways. What is modularity? Okay, one definition. It's breaking down software, breaking it up into pieces, and that's true, but that's a pretty naive and sort of useless definition. So reasoning about code in isolation, being able to reason about it. This is a goal of modularity, and so this is a bit more reasonable, a bit more useful definition that modular code can be reasoned about in isolation. Modular code has minimal dependencies, kind of, high cohesion, low coupling, that kind of measure, and that's something you can actually start to measure. So this becomes a much more useful definition in many cases. It's hard to measure that I've broken software down, but it's relatively straightforward to measure cohesion and coupling. Finally, the definition that kind of makes the most sense to me is that modular code is code that I can design, develop, repair, or replace independently or relatively independently from the rest of my system. And this speaks kind of a bit directly to what Sandra was talking about this morning. And this is why microservices seem great, because you can kind of pick and choose and match and just replace parts wholesale because they're extremely modular. And everything's talking to everything else over HTTP, so there's no type system in the middle. It's just things talking over the network. So in a sense, that's maximal modularity. So modularity plus testability, what's the intersection between the two beyond what we've kind of just discussed already? One is independent instantiation. If I have a very modular piece of code, something I can instantiate without instantiating the rest of the universe around that code, it's something that I can test in isolation. It becomes easier for me to just physically bring it up in the system and test it. It takes less time, it's easier to think about, there's less boilerplate, et cetera, et cetera. So that's one big relationship between the two. If I find that there's a lot of ceremony and a lot of boilerplate involved in bringing up a bit of code to put it under test, that should be a clue to me that I failed somewhere in my modularity analysis. Fewer distant dependencies. Though if I've got a nice modular system, I don't have a thing here depending on something that's 6 hops away, via some global variable or something along those lines. So I can be confident that what I'm testing, that what I think I'm testing is what I'm actually testing. And you can get into situations in complex, spaghetti code where I write some test that's supposed to prove some property of some bit of code, but what I'm actually doing is proving some property of this piece of code over here, and this code that's under test is actually broken. I'm sure some of you have experienced that. So highly modular code that doesn't have these big distant dependencies, is more immune to that kind of problem. Finally, modular code is easier to understand. There's less I have to hold in my head in order to comprehend what the code is supposed to do and to think about the states that it goes through when it does its job. And this allows me to have much more thorough testing. That is, that I can make sure that I've tested all the edge cases, I've tested all the mainstream bits, and I've tested all the error conditions, and so forth and so forth. If my code is too big and too complicated and it has too many far-spread dependencies, that becomes effectively numerically impossible to do. So what are you going to do with this knowledge now? How can you use this to help you guide your development process and manage your non-functional requirements? Well, an easy way is that if you find it pretty easy to write your tests, and you find that the testing process is painless and somewhat pleasant, which may be something that a lot of people haven't experienced, but a pleasant testing experience, then you've probably got nice modular code. You haven't got weird relationships gumming up the works, because if you had those relationships, your testing experience would be pretty painful. It would be something like this. You'd have this horrible experience where you never really felt confident in what you're doing. You never felt like you had covered all the bases. You had to spend all this time and energy just to write the test and then run them, and that takes a long time. So if you're having really bad problems in testing, it's an indicator that perhaps you need to look at the modularization of your system. Maybe you can break things into easier parts. And looking at what your tests are doing is a great way for you to identify where the cleaving lines need to be between your code. Because what do tests typically do, especially like unit tests? May have 100 tests, and they all kind of do the same thing and a little bit different. And when you identify what the pain point is in that same thing every time, that gives you an idea where to break your code in pieces. I'm talking at a pretty high, vague level here, but I think a lot of you will identify with this and recognize that you've seen this in the past. So use those indicators as keys to tell you what to do. Listen to your tests. Use the feedback from your testing experience to tell you where you probably have problems in your code. The next quality I want to look at is performance. Performance is not so obviously correlated with testability. And it's a bit of a stretch compared to modularity to compare them, but I'm going to take a go at it. It's often said that everything can be traded off for performance. If you need to make something a bit faster, you can get rid of some scalability, or you can get rid of some security, or something along those lines. And presumably, yes, you could trade off testability for performance. I don't suggest that, and that's not what I'm saying that you need to do. There is that relationship, but really it goes quite a bit deeper than that. Trading off performance for testability would be a very short-term gain, and one that would damage you exponentially in the long run. What you really want to use is testability as the key to hitting your performance goals. And I'll explain what I'm talking about, but basically, if you listen to your testability over the long course of a project, it allows you to make the proper design changes at the end to hit your performance goals. And I've seen this happen over and over in projects. Remember that you may be starting here, but that's where you need to go. You need to end up way down there at the end of the fjord. It's Lysebotn down there. So if you're optimizing performance here, you're probably going to get things wrong. I've seen this over and over again. We're very bad at predicting where the real hotspots in code are early in a design process. We think we know, and it's fun to spend a lot of time optimizing these bits of code, but often that's just thrown away. You spend all sorts of time trying to fix these little bitty problems with great big optimizations, so you may have made 0.01% of your code 1,000 times faster, but that has no real impact on the ultimate performance, the ultimate user experience. So you want to avoid wasting effort on incorrect performance optimizations early in the design process. Just accept that things are going to feel a bit suboptimal at first. It's going to rail against all your instincts as a developer, but if you want to make a product, if you want to make successful software, you need to have this, you need to fight that instinct. And finally, testability allows you to avoid unnecessary compromise. What I mean by compromise is compromising on certain qualities in order to get performance when you don't necessarily have to do that. So you want to avoid doing that early in the process if at all possible. So what does testability then allow me to do with performance? It allows me to monitor and manage my compromises. So as I go through the development of a system or a feature or whatever, I know what kind of damage I'm making to it as I go. The testability is giving me constant feedback on the effect of the changes I'm making so that I can know, okay, I've made some change that has an influence on performance or on scalability, and I know that now because I'm using all the tools at my disposal to figure that out, testability being one of those. And that's important. But the most important thing is that if you use testability properly and use all the tools at your disposal, by the time you get to the end of your project, when you really do understand all of your requirements and your entire deployment system and where the real hotspots are in your code, you'll be in a much better position to make the right changes, to make the changes that actually do give you the performance you need. You know, this whole notion of the Pareto principle where 80% of your time is spent in 20% of your code. This allows you to identify that 20% accurately rather than guessing at what it is early in your design process. So that's how testability relates to performance. Get a drink of water here. This next bit, scaling up development, is not really a software quality so much as it is an organizational quality. What I mean by scaling up development is you started off with a small 1- or 2-man project, a proof of concept, a prototype, and it's become successful. And your company has said, hey, we want to make this into something bigger, into a product. So you have to scale up the development effort surrounding that to turn it into something sellable, something marketable. Excuse me. An architect's job is very often to bridge technical and business ends of a company. They need to be very technically adept, but they also need to understand the business. They need to understand things like the market. They need to understand customer needs and requirements and so forth, and their job is to translate business needs into technical implementations. That is a great definition for what a lot of architects do. Part of that is managing this scaling up. Part of this is planning for that happening. So you may go from this small little team of one guy plugging away on something, and it becomes a popular thing. It might be productized. So it grows up into a team of, 7 or 8 people, something along those lines. It gets even bigger. So now it's turned into 2 teams that may be in separate buildings and maybe in separate countries. Pretty soon you get a separate testing department, or at least an existing testing department that's now paying attention to your code, whereas before they weren't. You may get new kinds of tests, integration tests and acceptance tests and things like that. You make it a documentation team. You can grow this as arbitrarily large as you want. The point is, this thing you started off with, this little 1 or 2 man project, is suddenly scaled up into something that has 100 people staring at it all the time. And if you're not ready for that, you could be in real trouble, because you could find it's going to quickly find the weak spots in your design. So where does testability play into this? It doesn't seem like an obvious relationship, except perhaps with the testing team. One is independent development. If I've listened to my testability throughout my design, and I've kept my design modular, we talked about earlier, it becomes relatively straightforward to take one module and give it to the team in the next building or in the next country over. The new people that I bring onto my team can develop with confidence because they've been given a code base that is not just testable, but is tested. They can know when they've broken things. Rather than handing them a blob of code with no framework, no regression suite around it, where they are going to break things kind of arbitrarily on accident, they've now been given something that they can change and know when they've made mistakes because the test system exists. And easier to integrate with existing infrastructure. This is simply saying, if I have a testing team that I ultimately have to hand things off to, it's nice to give them a working test suite and testable code that they can then manage and work with. So as somebody who might be tasked with eventually dealing with this kind of scaling up, it pays great dividends to listen to your tests throughout your development process, to make sure that you remain modular and to ensure that you do have the testing infrastructure in place when it comes time to expand into the larger organization you may be embedded inside of. I guess I could add to this, this is very similar to also selling a product. This is something a lot of us, well, we never learn about it in computer science education, but in the real world, selling a product is an important thing. Like taking the product that you developed and selling it wholesale to another company, IBM or Microsoft or something like that. If you go to them and say, well, we've got this blob of code, but it's not really testable, we don't have any tests, we think it works, here you go. They're gonna think twice about buying it because they're gonna spend a lot of money on it. But if you tell them, look, we have a complete regression suite, it's a high quality piece of software, we can prove it, they'll be much more willing to give you a lot of money for it so you can retire, which is my plan. So the solid principles, we're doing really well on time here. Who knows what the solid principles are, or has even heard of them? They're object-oriented design principles that have come out of basically our decades of experience writing object-oriented software. And so we'll look at each one of them in turn and look for stronger or weaker relationships with testability as we go. Oops, how's that? Okay. So these are the solid principles here. It's an acronym for single responsibility, open, closed, Liskov substitution, interface segregation, and dependency inversion. Single responsibility basically means do one thing and do it well. Don't have a class that does 10 different things all at the same time, but have one that does a single thing well. It's a high-level rule of thumb that you can follow. It's not a metric that you can actually measure, but it's something to keep in mind. Most of you, I've definitely seen classes like, most of you have probably seen classes like this throughout your life. It's got a vague name, component object. It sits at the root of some monstrous class hierarchy. And it sort of does a little bit of everything, right? This has grown up with some product somewhere, and now it's got a render function for things that can render themselves. It's got a serialize function for things that serialize themselves. Is alive, dealloc, kill, blah, I've just made up some names, but these probably all map onto things you've seen. This is a really big, complex class that's hard to define and hard to describe. It does way more things than it probably ought to do. It's called a God class sometimes because it's the root of whatever your system is. You end up with relationships like this, hierarchies of classes like this, where you've got the compound component object and main view and storage manager that all have to inherit from this for some reason in your system. But really, you would never treat these as, you never treat storage manager and main view the same anywhere. This is just an accident of the complexity in your system. And this is a failure of single responsibility. And how does this intersect with testability? It should be pretty obvious how this intersects with testability. How many tests do I need to test this? Who knows, right? I mean, a lot of it depends not only on the fact that it's a huge complex class by itself, but there's all sorts of polymorphic behavior going on in here, right? Every one of these is probably overridden sort of arbitrarily in this huge complex tree that I've got going on. So it's really hard to know how to test this. What's the expected behavior? If I call, activate after I call dealloc, what does that do? It's really hard to say, because some things probably won't do anything when you call deactivate on them. Other things will probably, shut down the main reactor. Who knows? Star Wars reference. And what are the interactions between all these things? This is really just, this is an exponential explosion problem. We don't know what's going on in this class because it's just too big and it just does too much. This is a failure of single responsibility, and it shows up in testing. It shows up immediately in testing because you'll know you're not getting it right. You will sense in your gut that you have no way to test these things properly, and you need to listen to that feeling. Now, there might be ways to break this up. I mean, this is a really hard problem. A lot of people are in this situation, and it's hard to get away from. But you could imagine breaking this up into a displayable, serializable, activatable, maybe some other classes. But the point is not how to fix the problem. The point is how to recognize that it's there. The next solid principle is open-closed. Open-closed basically says that classes should be open for extension. You should be able to add features to a class through inheritance, essentially, but closed for modification. So if I want to extend the functionality of a class, I shouldn't have to change its source code. I should be able to add source code and use some, a template or something along those lines to get the behavior I want. That's what open-closed means. There's a really interesting relationship between open-closed and testability. So here on this is your left side, you've got a switch statement that's telling you the speed of different types of birds. There's a European swallow, African swallow, and the Norwegian blue. And if you want to add a new type of bird to that list, you have to come in and modify this code. On the other side, you've got a very normal, standard, simple relationship using inheritance. Does anybody know what this math is here? Well, this is McCabe complexity. This is measuring the number of paths through that code. McCabe complexity is a very interesting topic in its own because it tells you something about the complexity of a body of code, and you can use it as a static metric to tell you if you've got things that are too complicated in your system. It's really interesting to read up on. One interesting quality of McCabe complexity is that it gives you a lower limit on the number of tests you need to write to test something fully. So this 7 here tells me I need at least 7 tests to look at all the paths through that code. The number over here is 3. So clearly, this takes twice as many tests to test as that, and it's a mess. I mean, it requires that it's going to call for larger recompilations because I'm going to have to touch some core thing. So there's this is something that it's good to keep in the back of your mind. Try educate yourself on McCabe complexity. I mean, that's the formula there, but it's all over the web. You won't have any trouble finding information on it. But it can inform the way you think about your code, and it can inform the way you think about scaling down the complexity of functions. It becomes a reason to do that rather than, it becomes a mathematical reason to scale down the complexity of functions rather than a mandate from somebody who's wiser than you. There's a great quote related to this. This is from Rob Galanakis, who was, I don't know if he's still there, but he used to be the technical director at EVE Online. How many if statements does it to feature? If that number is high, then you've got a problem with your open close because you have to open up a lot of things, a lot of bits of code to spread some feature into your system. But if you've got a nice extensible open close based system, that number can be 1, it can be 0, because everything happens through polymorphism. Liskov substitution. Barbara Liskov came up with this term. Basically, you can replace the use of a base class with a derived class, and the behavior will stay exactly the same. It's not just saying that the interface stays exactly the same, it means that the behavior stays exactly the same. And this is a key point that's often missed in discussions about Liskovs. So its intersection with testing is a bit like this. So I've got a base class and a subclass A, and I write a test against the base class, but the only concrete instance I have is subclass A, and my test passes, everything is fine. Until somebody comes along, they add subclass B, and my test starts to fail. This immediately tells you that you have violated Liskov substitution. Because anything, including this test, that works for base class should work for all base classes at all times. If this fails, it means that you either don't understand what's going on in here, or you've made a mistake in subclass B and not preserved an important behavior. I mean, behavior preservation is difficult. We don't have compilers that can help us solve that problem. Yeah, all the compilers can do is tell us that our interfaces match up, but they don't know anything about behavior. This is a big unsolved problem in computer science. But if you find this is happening, it means you violated Liskov substitution, and you need to ask yourself if that's important to you. It ought to be. It's proven itself time and time again to be an important quality in object-oriented systems. Right, so this is the state you want to get to where everything works. Interface segregation, prefer cohesive, focused interfaces. So you want an interface definition that talks about just one little thing, and you want to be able to pass that around rather than passing out big fat interfaces. This is related to the single responsibility interface or principle that we talked about earlier. So imagine you have a system like this. You have iKitchen sink, and okay, I don't know if that's a metaphor that rings a bell, but in the United States, you say throw in everything, including the kitchen sink. It means you throw in all sorts of complexity and silly things like that. And you've got my class as a subclass of iKitchen sink, probably only using a subset of its interface. If you're using mocking in your testing and you want to mock iKitchen sink, you've just bought yourself a huge amount of effort because you have to mock everything that iKitchen sink does. And because of list call substitution, I want to call it LSP sometimes, because of LSP, you have to mock all of its behavior as well. That's really, really difficult work. And it means that if iKitchen sink ever changes, not only do you have to worry about my class, but this big mock you've created over here. Like I said, that's a lot of work. You want to avoid that kind of work. So if you find in your testing efforts that your mocks are starting to consume vast amounts of effort to create, you should step back a second and see, can I break up the things that I'm mocking into smaller bits? This is a good clue, a good signal to you that you have got things that are too complex and are too much effort. It's not always the case, but it's a great thing to listen to, and if you're ignoring it right now, you're doing it to your own detriment. The final principle we'll talk about is dependency inversion. So depend upon abstractions only. Don't depend on concrete instances of things. And low-level things depend on high-level interfaces, and high-level things depend on low-level interfaces. Everything communicates through dependencies. You've probably all heard about this in one form or another, dependency injection, all that kind of stuff. How does this play into testing? So imagine I have this bit of functionality here, a relay message. I want to send a string. Well, in this case, I want to send it to a satellite uplink. And you can imagine instantiating a satellite uplink that actually works is a lot of effort because you have to align the satellites, you have to align the dishes and send messages, and it's expensive and all this kind of stuff. So to test this, you've created a very expensive testing situation, and for no real gain. What you can do instead is rely not, oh, sorry, let me just finish that thought, is rely not on the concrete satellite uplink, but depend instead on an interface, in this case, relay. And in the case of real world, you would use a satellite uplink, and in the case of testing, you could use just a mock relay. I mean, this is very common sense. I'm not telling most of you anything you've never heard of before, but in the testing, it can come out in testing that you've got things that need to be abstracted into interfaces, and this is yet another signal that comes out from the solid principles to tell you, listen to your testing. So those are the solid principles and their intersections between with testability. Of course, you could think of more. I mean, this isn't an exhaustive survey of this domain. But one thing it tells you is that solid code is generally going to be testable code. We've seen how having the solid principles applied to your code make them generally more testable. Testable code is probably solid. So if this is one of your criteria for release or something like that, one of your quality criteria being solid, then if you have nice testable code, you're probably following the solid principles, or you're using a functional language, in which case it makes no sense to talk about that. There's an interesting talk by Steve Freeman and Nat Price called Building on Solid Foundations that talks about some of this same kind of stuff. If you ever see them at a conference, and they go to lots of conferences, you should go see their talks. Actually, no matter what they're talking on, you should go see their talks. They're very, very bright guys. I think they come up later in this talk as well. Finally, we'll look at modifiability. So Mr. Potato Head is extremely modifiable, right? And you can put ears and eyes and hats and stuff all over him. So he's the poster boy for modifiability. What do I mean by modifiability? It means the ability to modify a piece of code quickly and safely, or I say a piece of code, some piece of functionality quickly and safely. So you can do it in a predictable amount of time, and you could do it in a way that you're pretty sure you're not breaking the rest of the world when you do it. So like testability, modifiability kind of lies on a spectrum of easy to hard. The relationship is not entirely straightforward, but it's worth looking at because it's kind of interesting. So if you look at this chain here, modularity implies that you have low coupling, which means you have low ripple through your code. When you make a change in one place, it doesn't necessitate changes throughout the rest of your system. And that's obviously more modifiable because you can do it more safely, you can do it under testable conditions and so forth and so forth. This is one of the main reasons you want modularity in your code. Likewise, if I have solid code, my code is easier to understand because it's following some certain patterns that everybody understands, which means that the modification is simpler. I know how the pieces fit together at a higher level than just interfaces and raw code. I have principles that have guided the way I've put my code together, and it makes it easier for me to reason about broader changes. So this intersection between modifiability and testability is essentially kind of, it's two steps removed in some sense, but it's an important one. Because if you find that if you're trying to modify your code, and it's really painful to do, it's because you've ignored some other things in your code, and maybe you should have listened to your tests before. More importantly, however, much like performance, strong tests allow you to make changes safely and allow you to make riskier changes much more quickly. And this comes into play quite a bit. You've reached sort of the end of a feature development cycle, and you've kind of you found a bug. And you say, okay, well, I can fix this bug by inserting this horrible hack here, and I'm pretty sure it'll work. Or there's a more systemic change I can make that's going to necessitate changing more code, but it's actually the right thing to do in the long term. If you don't have a test suite and you have no way of detecting when you've broken things except for pushing buttons on your keyboard, you'll probably go with the hack, and that accrues over time. You do that again and again and again. But if you have a nice testable system with a nice regression suite built in, you'll be much braver, much more willing to make the right change to your system, and that's the long-term, economically sound thing to do. So the intersection between modifiability and testability is that monitoring your testability allows you to make the right changes at the end of, or late in the development cycle, much like the performance stuff we were talking about earlier. Ultimately, it lets you make the best changes. That's the most important thing. Right, okay, so we're doing well. So we've kind of examined some of the intersections between software qualities, organizational qualities, and testability, and I hope that it all makes some sense. I hope I'm not just kind of sound like I'm making stuff up, although I kind of am. So let's look at a few applications of this in the real world. We'll look at agile methods very quickly, test-driven design very quickly, and domain-driven design very quickly as well. So this is kind of how I see agile in a sense. Agile, no matter what flavor you're working with, no matter what Scrum or Kanban or whatever, it all has to do with getting feedback quickly in iterations, processing feedback, and correcting your course over time. The mechanisms you use to do that, there's a lot of debate around that, but the idea of iterating quickly is very important. And so it happens in a sort of fractal way. You have this large-scale notion of sprints and reviews and blah, blah, blah. And inside that, you've got your stand-up and the work you do at your desk. And then the individual developer is, got tests at their desk, and they're constantly processing feedback. So at all scales, you're processing feedback very quickly. Testability is a signal that's present in all of these cycles. Right? You're getting feedback at your desk when tests start to fail, or when you're trying to write tests, or when your tests are really complicated, or they take a long time to run. You're getting feedback at your sprints because you look at your burn down chart and said, well, I would have had that feature finished, but I had to spend 3 days writing this test because the satellite relay is really expensive. And at the planning phase, you should be keeping track of the amount of time you spend in various aspects of testability, all of your development processes for that matter. So by quickly processing the signals you're getting out of testability at all these levels, you are pumping a lot more information into your decision making. And your developers get more effective, your teams become more effective, and your design cycles become more effective. It's pretty straightforward. I'm just saying there's more information you could be paying attention to that you're probably throwing away right now. And you're not alone. This is, thank you, all over the world. So remember that, again, Nusafjord, that's where you're going, and that's where you start. That's how long your code needs to stay. I'm going to put that in quotes. Your code needs to stay agile. It needs to stay malleable. It needs to stay in a state where you can make the changes you want to make. Because if I get feedback right before I get to the end there that tells me, X should really be Y, I need to be in a position to turn X into Y. And if I've let my code accrete all sorts of cruft all over it, or I can't make the change, or I can't make it safely, I won't be able to make the change, and I'll have upset customers, or no customers. That would be horrible. Test-driven design. There was mention of TDD earlier in Thomas's talk. Yeah. So this is the standard TDD loop. Whether you use TDD or BDD or star DD, it doesn't really matter. The idea is typically the same. You make something fail, write something that tests a feature that doesn't exist, write the feature, and then refactor. Write the test to pass, and then refactor. And if you've ever really studied this stuff, there's also this little kind of back loop here. Because you're doing work here, writing a failing test may make you realize that you need to do some refactoring. So it's good to keep that in mind. This really speaks directly to what I'm talking about. let me just read this note here. Yeah, this little loop, this sub-loop here, is where you're paying attention to your testability experience, right? Here, you're writing tests. You're trying to make your tests do things, and you're experiencing the pain or pleasure of doing that. And that's when you start to feed that back into your code. Whether or not you're worried about some feature, you're really worried about refactoring your code to make testing work better. So this is a channel, a really powerful channel for the testability feedback to come into your system. It's a really simple relationship, but again, not everybody knows about this. If you ever read, speaking of Nat Price and C. Freeman, this book, this diagram just comes straight out of that book. And these are the guys that invented this stuff, right? So it pays to listen to what they have to say. So the relationship between testability and TDD is pretty obvious because TDD, you're always doing tests. It's central to the discipline. So yeah, there's this implicit relationship between testability and TDD, which is that testability is always a focus when you're in TDD, and the benefits of what I'm talking about are sort of built into the process. I mean, TDD works in part because of what I'm talking about here. But you can make it explicit as well. You're in a great position, if you're doing TDD, to use testability, to talk about testability in your stand-ups or in whatever retrospectives you use, because you're paying so much attention to it. And this refactoring loop that we talked about earlier, this little sub-loop, becomes very, very important in the situations. So TDD strength is based on a lot of the same ideas I'm talking about here. Yeah, I think we got enough time. DDD, one of my favorite things ever. Memorize that picture? Okay, so basically, don't memorize it. DDD says you're going to center development activities around a core domain model and implementation of that domain model. It's a really powerful technique that I'm not going to get into very much. But if you want to read about it, I highly suggest both of these books. This is, it should be up here too. Von Vernon has a new book implementing DDD. It's an incredibly good book. The point is that you've got this thing in the middle, the domain model, that's independent of things like storage technologies, not programming languages generally, but all the other things that fit into a development process. A domain model in DDD is extremely testable. It has high cohesion inside itself, but essentially no coupling to the outside world. So it's something you can deal with and manage without worrying about whether you're using MongoDB or DB2, or whether you're using some testing framework, or whether you're using Google frame buffers or Corba or whatever. It's all almost irrelevant. And because it's so testable, it's hard for me to verbalize exactly the relationship, but the point is that you've got this nice testable core, and DDD has lots of great qualities that come along with doing DDD, and those qualities follow from exactly the things we're talking about in this talk. The relationship between modularity and testability, the relationship between modifiability and testability. They're all present in DDD. And these are really strong reasons to consider using DDD. If you've never looked at it, or you've looked at it but never used it, it's really worth testing out. Do a little toy project with DDD, and you'll realize the benefits, I think, very quickly. It's fascinating technique, well worth looking into. So that's really all I've got to say. What I'm going to close with are some quotes from people who, maybe they're smarter than me. I don't know. They're better known than me, so maybe you'll believe them if you don't believe me. Uncle Bob, what does he have to say? One reasonable definition of good design is testability. It's hard to imagine a software system that is both testable and poorly designed. It's also hard to imagine a software system that is well designed but also testable. So he summed up this talk in a paragraph, so that's why he is who he is. John Lakos, one of my all-time heroes. Design for testability is of paramount importance when successfully constructing large and very large C++ systems for exactly these reasons that we've talked about in this talk. Michael Feathers. There appears to be a synergy between testability at the unit level and good design. If you aim for testability and make some good choices, design gets better. If you aim for good design, your design becomes more testable. Hopefully you believe them. If you don't believe me, there's a lot to this. That's all I've got, and I'm happy to talk with anybody about this after this. Thank you.